It's very important for our later work with Lie groups and Lie algebras for a person to be familiar with the indices that are used with vectors, tensors, and scalars. The metric, especially an indefinite metric, and the difference between covariant and contravariant vectors and indices, the ability to raise and lower those indices, and so forth. We will proceed with our work in this direction. We now have position and velocity and a way to take a derivative using the proper time by defining relativistic energy and momenta. We define the relativistic momenta, p mu, to be by definition the mass m times the forward velocity v mu. So it is taking our previous definition of the four components of velocity and multiplying mass by each one of them, we get mc divided by the square root of 1 minus v squared over c squared and mv over the square root. We define the energy in relativity to be E over c times this term p naught, which is the zeroth component of the momenta. And this other component here is defined, of course, as the regular momenta. We can see that the momenta in relativity differs from that Newton would use by this additional factor 1 over the square root of 1 minus v squared over c squared. That does alter the momentum. And at very high velocities, of course, since this factor down here approaches zero, this makes the momentum huge near the speed of light for a particle, much larger than what it would be otherwise. In fact, you can see that a particle moving, even an electron, right at the speed of light could have a momentum greater than an entire planet or a star or even a galaxy, and in fact infinite. That's one of the reasons that it's impossible to take a particle that is moving slowly and accelerate it up to the speed of light, because it would take infinite momentum, and it turns out also infinite energy, more than is available in the entire universe. In this equation, we explicitly defined E over c to be p naught, or mc divided by the square root of 1 minus v squared over c squared. Multiplying both sides of this equation by c, we get the famous formula E is equal to mc squared divided by the square root of 1 minus v squared over c squared. We can expand this lower term by the binomial theorem, and the reader should do that, by taking this and writing it as 1 minus v squared over c squared to the power minus 1/2, representing the division for minus and the 1/2 for the square root. And if you do that, you'll be able to get all of these different terms. The first term, of course, in the binomial expansion is just mc squared itself. And this famous term, formula, E equals mc squared, obtains when one has the velocity is equal to 0. Of course, one can see that here also. If v is equal to 0, E is equal to mc squared. This is called the rest energy of the particle, and it is the lowest kinetic energy that a particle could have. We notice by contrast with Newton that, in fact, the lowest energy a particle can have would be 0. So this is already a difference, this rest energy of a particle, or an energy that is contained in something by its sheer existence, is something that relativity predicts that's really, truly phenomenal. It is appropriate that in the next order of magnitude, in addition to that constant amount, we see that we get a 1/2 mv squared, thus reproducing exactly what Newton predicted for the kinetic energy. And here is the correction, the first correction to that, meaning that at higher speeds, relative to the speed of light, there's another term that augments the kinetic energy. So actually the energy is a little bit larger than we would anticipate. As we normally only take energy differences, as long as this is constant and we're not converting mass into energy and vice versa, then it follows that this kinetic energy is going to work just fine for all of our equations until we begin to get near the speed of light, when these higher order terms become involved. It's very interesting to look at the length of the momentum vector. Here we take g mu nu, p nu, and do this contraction, which of course is nothing but p P lower nu, if we think of this one as being lowered to a lower nu, P upper nu, this is a way to write the scalar product very often as a lower index contracted with an upper one, and it really is just a way of getting rid of the metric and burying it in a covariant vector contracted with, and when we say contracted we mean that the two indices are identical and they are summed. P lower 0, P upper 0, and so forth must have as their length the momentum squared, 4 momentum squared, must be m squared c squared. This follows immediately from the fact that the momentum is the mass times the velocity, and the length of the velocity vector was c. Therefore, since the length of momentum is mass times velocity, the p squared must be m squared c squared. This must be equal to, using this format for the 4 momenta, e squared over c squared minus p squared. This formula here is of incredible importance because it corresponds to the Newtonian connection between energy, mass, and momenta in the relativistic case, where in the Newtonian theory we had E is equal to p squared over 2m for the non-relativistic Newtonian situation. So we now have a really different connection between the three. It's not even obvious from this equation that we can take this equation and get this equation out of it, although we have already seen that right here the connection through E is equal to 1/2 mv squared is obvious at low velocities where the difference of the constant energy does not play a role. It is of the greatest importance here to note that the mass is a scalar. One of the most universal mistakes that's made in trying to understand relativity is to think that the mass has associated with it the square root of 1 minus v squared over c squared, and this is called a relativistic mass. There is no such thing as a relativistic mass. The square root of 1 minus v squared over c squared, 1 over that, was in the velocity before the momentum was ever formed, before the mass ever played a role in the situation. This square root comes from the ratio of the two clocks. It comes from the space-time origin. It does not originate in any way associated with the mass itself. It is easy to think that because in doing just simply momentum conservation, it's easy to think of taking this m and associating it with its square root here and here as being the factor that multiplies c and v in looking at 4 momentum conservation. But that is not the case. The m came after the square root was already multiplying the c and the v. So again, I emphasize that the mass is an invariant mass. It is always a scalar. It transforms as a scalar from one frame to another, and there's nothing that corresponds to what we call, in some texts, a relativistic mass. We can learn some incredible things from that equation. We can actually classify elementary particles, or things that can exist in our universe, by this equation, e squared c squared minus p squared is m squared c squared. I want to first consider a particle that's at rest. If the particle is at rest, then even in relativity it has no momentum. Therefore it follows that e squared over c squared is m squared c squared. Or, multiplying by c squared and taking the square root, we get E is equal to plus or minus mc squared. Now we've already discussed the fact that there's an energy associated with the rest mass itself, E equals mc squared, as Einstein has taught us. But here we're getting something else. We're getting a possible negative energy. Everyone neglected these negative energies for a long time after the founding of relativity, thinking that they were just some type of spurious mathematical solution that was erroneous. However, when Dirac worked with relativistic quantum theory, he found that although he could eliminate the negative solutions in starting the equations out, that later on those negative solutions would creep back in, and that he couldn't eliminate them altogether for all times. He therefore made the conjecture in 1928 that the negative energy states corresponded to a dual kind of matter that he called antimatter. And that matter was to have the same mass but the negative of charge and other quantum numbers associated with a particle. It was only a short time after that experimentation was able to create an anti-electron that did in fact annihilate the electron, and that particle was called the positron. It had the identical mass, and when it came together with an electron, it could totally annihilate it. The electron and the positron had the identical mass, but they have opposite signs of the energy and opposite quantum numbers like charge and any other type of quantum number they may have. They are able to totally annihilate each other into pure energy. And anytime matter and antimatter get together, that is a possibility. Conversely, one can, out of pure vacuum with energy, create matter and antimatter, a particle and an antiparticle. And in fact, we find that this actually happens, and where particles spring into existence along with their antiparticle in a process called vacuum polarization inside the atom. We also want to consider now units where the velocity of light c is equal to 1. And this is just a convenience. We choose, in other words, a length of a meter that's exactly 3 times 10 to the 8th of our regular meters. And in that unit, c is equal to 1. That just lets us work with this equation in a little bit easier fashion. Here we see that we now have, with c is equal to 1, e squared minus p squared is equal to m squared. And we can solve that equation for m and wonder the same thing. Gosh, we get 2 square roots. Is it possible that there's something called negative mass? It's certainly allowed by the theory of relativity here. A negative mass is thus predicted and not contradicted, at least at this point. Presumably, it would represent, in a gravitational equation, a force in the opposite direction. And thus, if we had an object that had a negative mass, it would fall upward in a gravitational field and thus represent anti-gravity. No such particles have yet been found, but back in the 1950s, it was believed that maybe antimatter, like an antineutron, also would have negative mass, as well as negative energy, and fall up in a gravitational field. That was found to not be true. So, negative mass is one other new thing that we can predict out of these equations, but does not seem to exist, at least at the present. We get 3 more classifications for the particles by going back to this equation again. We now look at the definition of the mass where the mass is considered positive. And this equation right here gives us, as always, when we have the square root of the difference between 2 squares, 3 cases. These 3 cases are as follows. Energy is greater than momenta, energy is equal to momenta, and energy is less than momenta. If energy is greater than momenta, then mass is a real number. Obviously, because this is greater than this, and it's the square root of a positive number, and therefore it's a real positive number. One can show that for such particles, the velocity is always less than the speed of light. These are things like our regular electrons, protons, neutrons, chairs, tables, apples and oranges, and ourselves. Then there's another class of particles where E is equal to P. If E is equal to P, the mass is 0. One can show in those cases that the velocity of the object is exactly c. It can't be faster and it can't be slower, according to the theory of relativity. These particles, examples of these, are the photon itself and the graviton. Finally, we have another class of particles where the energy is less than the momenta. Mass then becomes an imaginary number, and one can show that the velocity is always greater than c. A missing right there in the always. V is greater than c always. These particles are called tachyons. None have been found yet. They permeate space in the same way that a regular particle permeates time, or they have their existence spread out in space. They're spatial, just like regular matter has their existence spread out in time. Now that we have position, velocity, momenta, energy, time, proper time, and mass fully explored, we next want to turn to the tensor level and to discuss the relativistic electromagnetic theory. As one might guess, relativity is very natural form of expression for the electromagnetic field, since the electromagnetic field is inherently relativistic. The way that we have normally written those in terms of the electric and the magnetic fields is not the natural way, it turns out, to see these things. Rather, the electric and the magnetic field are two manifestations of the same thing. We will postulate the relativistic form, and then we're going to derive from that the traditional form of Maxwell's equations. So I'm going to begin here with a tensor form that's relativistically covariant, meaning it has a manifest relativistic tensor form, and we're going to take that and derive from that the regular Maxwell's equations. Obviously, you could take all of these equations and reverse them and go in the opposite direction and get the relativistic form from the non-relativistic expression. The first of these equations is a definition. I define the totally contravariant antisymmetrical second-rank tensor, called the electromagnetic field tensor F mu nu, by the following equation. F mu nu, where mu and nu go 0, 1, 2, 3, and this would be row 0, 1, 2, 3, column 0, 1, 2, 3. So this element right here is the 0, 1 element of this tensor. And these components, although they are slightly difficult to read, are Ex minus Ex over C, minus Ey over C, and minus Ez over C. And of course the negatives down the first column. The diagonal is 0, as required by an antisymmetric tensor. And the spatial components are defined as Bx, By, and Bz. These two with negative components, and this one over here with a negative component. We define now two related concepts that we need for the electromagnetic field. What is called the 4 potential, A mu. We define that vector as the field potential, the potential phi divided by C, and the potential vector A. And we also define another 4 vector called the 4 current J mu, where J naught is C times the charge density rho, and the current density J forms the spatial part of that. We can relate F mu nu to A mu by the following equation. If it is true that an electromagnetic 4 potential exists, then it follows that F mu nu is equal to the partial mu of A nu minus partial nu of A mu. Now this partial mu right here, I should comment on. The partial mu partial with a lower mu is actually defined as the partial with respect to x upper mu. In other words, it turns out that when we take the derivative with respect to one of the components of the position, then even though this is contravariant index, the derivative with respect to that becomes something that transforms like a covariant object. Therefore, this is just a symbol that enables us to write this in a very succinct fashion. Likewise, if we lowered this index, it would raise this index, and that's what we have used right here. We have defined F mu nu as partial mu A nu minus partial nu A mu because both of these indices are defined as upper. We are going to write Maxwell's equations as partial lower mu F upper mu nu, of course there's a summation over mu, is equal to mu naught times J nu. And Maxwell's equations are defined in this way here, that the time derivative of the momenta with respect to proper time are equal to E, the charge on the electron or the particle, divided by c times f mu nu, velocity in direction nu. Now this is a beautiful expression when you stop and think about it, that if the electromagnetic field can be written in this form, then these equations right here give us all of Maxwell's equations. And that is a very succinct form. Over here are the derivatives of space and time of all the electric and magnetic fields, and they're proportional to, with a constant mu naught, the vector made up of all the charge and current densities. Likewise, just as here the charges and currents are giving rise to electric and magnetic fields, we can see, and their derivatives, we can see that the time derivatives of the momentum of particles are shaped by how the particles are moving. This is a generalization of the Lorentz force equation, and we shall see that also. So the main thing that we have to do now is take those equations and derive explicitly the standard forms of Maxwell's equations, the connections of the electric and the magnetic field to the potential, the scalar and the vector potential, and to show how these latter equations right here give rise to the Lorentz force, and in fact how this is a generalization now of what we would write if Newton's equations could be put in a relativistic form. We would have to take the four momenta and take the time derivative with respect to the proper time with these equations. The only way to really get a feeling for these equations is to sit and to derive through these actual derivations that I'm about to do. And then one begins to get a feeling for the upper and lower indices, for the tensor form, and for how you actually manipulate these equations. It's very easy to be lulled into a false sense of security by writing these simple equations, when actually underneath these are very long and involved equations in which we have encapsulated a lot with very special index notation and the Einstein summation convention.